Okay, Kelsey and Bree, yeah, we went over the packet, the 2011 free response. We'll look at those on the bus tomorrow on the way to the game. And now we've just started writing these notes on differential equations. So you might want to pause it at this point and write this down. All right, thank you. So number three, the types that we can't solve, all right? And what we did before is we said we would verify the solution, right? We would verify something. We're not going to work on that right now, okay? But that's where we did the T-chart thing. We showed that something really was a solution. But this is where this approximation comes in. This slope field thing we're going to talk about is going to come in. Okay, you got some sort of equation we don't know how to solve. It's not a memorized one like the other two. And so we'll just do a slope field. We're going to do a slope field to approximate the solution, okay? And so that's where that would fit in. We can also do a slope field for any of these others too, and we will. We'll actually do it on one where we could just solve it, all right? And we'll do a slope field just to kind of show what that's about. All right, but first of all, let's talk about Newton's law of cooling. So we got these two things. We got Newton's law of cooling, and we've got slope field. So first, Newton's law of cooling. All right, so there it is again. I wrote it up there. Same thing we had, that we just did. So you got y prime, the differential equations, y prime equals k times y minus t. The solution to that is y equals t plus a e to the kt. That's what we work with. Remember, in a differential equation, the solution is what we work with. Because what we want to know, I mean, let's say we have a cup of coffee sitting on the table out here and it's cooling in this room. We want to know how hot is it after 10 minutes? How long will it take to get it down to 80 degrees? Those are the kind of things we want to know. And so we need the input variable, little t, we need that in there, the time element, because that's not in the differential equation. So we need the solution to the differential equation to work with. All right, and here's a graph of it, by the way. You can kind of see how that would represent that situation. The coffee temperature is going down. I got Y, here's the temperature of the coffee. Big T is just this constant, this room temperature, is what big T would be in this situation. All right, and the coffee's just the temperature's gonna go down, 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 until it's eventually gonna get close to the room temperature. Okay? And the closer it gets to the room temperature, the slower it will be cooling as well. Right? Okay. I think somebody asked about our last quiz, said it had a problem kind of like this. Remember that one with the K, and we had to describe whether K was positive or negative? It talked about this situation, actually. Which I haven't passed back those quizzes, by the way. It's kind of on purpose, because next week when we get into this, after we've worked with this a little bit, then we're going to come back and look at those. Okay? So, anyway. So here would be a problem. So this is what we want to do. This is what you're going to have to be able to do on the next quiz. All right? Is we're going to have to be able to work a problem, a situation like this right here. Okay? So we've got some hot coffee sitting here on a cup. It's 190 degrees when I pour it. Fahrenheit. That would not be good if it was Celsius. That would really be hot. This is 190 degrees Fahrenheit. That's pretty hot. I mean, yeah, it's still pretty hot. But I mean, it's not boiling, right? Isn't it 200 and something? 212 or something? Okay, so it's not quite boiling, but it's hot. And the room is 70 degrees. Pretty close. And after 4 minutes, it's 170 degrees. Now, we have to have that piece of information, right? Because that is how we're going to find what K is. Right? In our solution, we have y equals ae to the kt, or the big T is in there too. And the K is the constant that determines the rate of the cooling. And that's based on multiple things. Some of you are in AP chemistry. It would be based on the chemical properties of the liquid. Right? It would be based on the insulating properties of the container. If it's a styrofoam cup, it might cool at a different rate than if it was just like more of a cardboard type cup, okay, or a ceramic mug or whatever. Actually, you have a homework problem. One of your homework problems today is going to compare that. You're going to have a situation 2 cups of coffee, one's in this kind of cup, one's in this kind of cup, and then you're going to compare the rates of cooling and so forth. Okay? It's another like your authors like to do, the characters in the problem are Boris and Natasha, which again, I think Mr. Manson and I would know, and I don't know if you guys would. Boris and Natasha. You ever heard of Rocky and Bullwinkle? Okay. Well, anyway, Boris and Natasha are kind of are they Russian? They're like, they're supposed to be like Russian, the enemies, whatever. Anyway, so when you read the problem, you understand. All right. But the questions we would like to figure out here, a couple questions you might want to know is how hot it is 9 minutes later, all right, after it's poured, and how long will it be until it's down to 100 degrees, okay? All right, so we're going to start with our solution to our differential equation. Now, the differential equation has big T, A, little k. What do we know so far that we can plug in right away?
Big T.
Big T is 70. What about A? Good. We can't find A right away. I was afraid some of you are going to say 190, right? A is not the initial condition like it is in a regular just A e to the KT problem. Some people do that way too early. Okay, so the 70 we can plug in right away. So go ahead and write that down. So 70 is the big T. That's the room temperature. All right, so we put that into our initial condition, or excuse me, we put that into our solution to our differential equation. And on the AP test, that's what you're going to do. You're just going to go right to that. You're going to recognize, hey, this is a Newton's law cooling problem. It's the only kind we're working on right now. And this is the equation I have to use. We don't really even have to use the differential equation. We only use the solution. All right, now what can I plug in to help me find some of these missing pieces, the A and the K? I could plug in this, but there's one I ought to plug in first. I ought to plug in y of 0 is 190 because that's a really nice thing to plug in. 0 is always a good thing to plug in if I can. So that's what I would do first. And so where do I put the 190? In for the y. Okay, so let's do it. So we would, I think your work ought to look something like this. So we plug the 190 in for y, and we put the 0 in for t, and I know some of this you could do in your head, and that's okay if you do, right? It's okay if you do. But, because now what's going to happen, you're going to get e to the 0, which is just 1, and so you're going to get a is 120, right? You're going to e to the 0, which is 1, you're going to solve for a, you're going to get a is 120. And so then you've come over to here, and now we've got it down to this part. Okay? Now we've got it down to that in the red. Right? So we found big T was 70. We found A by plugging in our initial condition. Remember we called these initial value problems, IVP, initial value problems. You have a differential equation, then you have an initial condition that you got to throw in there. All right. So now we get to here. We don't know what K is. Now we use our other condition we know. And that's what I was talking about earlier. You've got to know something about how fast it's cooling. Otherwise, you're not going to be able to find it for the rest of the way. So now we're going to put in 170 for y. We're going to put 4 in for t. And now we've got to solve this. Now here's where you can go to your calculator. Right? On the quiz next week, we'll be able to do our calculators with this. We just did one on that practice test where you had to do an LN and all that stuff. You can just go solve this right now. So why don't we go ahead and try that? Practice that real quick here. Okay, so we just go to our solve, type in the equation, solve for K. I would say a decimal would probably be preferable just because the solution without a decimal is kind of messy. But either way, yeah. And I would go ahead and keep 6 or 7 decimal places because remember we're going to now plug this back into our equation and we're going to use this to answer some questions and we want our questions to be accurate out to at least 3 decimal places. And so the more decimal places we carry on, we don't want to have a rounding error. So I usually write out 6 or 7. Okay. At least when I type them in. Now on your paper, you don't have to write out 6 or 7. But when I type it into my calculator here in a minute, I'm going to want to do that. All right. So let's go to here. So now we've got this situation. We've got our equation. We've got our K value. We now have the full solution. Now, in differential equation lingo, the first solution we had is called the general solution, where we didn't know the A or the K. That's the general solution. Now we found our specific solution for this particular situation. So our specific solution to this differential equation is here. So now, how hot is it after 9 minutes? What do we do? Plug a 9 in for T, right? Plug a 9 in for T. So I think it's good to write it out. I don't think it's necessary, especially when you're just plugging in a 9. Matter of fact, and we've been talking about communicating your mathematics and showing your work. I think if you just did that, that's okay. Y of 9 communicates what you're doing. Now, you better have Y written out on your paper, right? You better have your Y equation written out on your paper. What you've done is you've communicated that Y is defined to be this. And then when you write Y of 9, you're telling me and the person grading your AP test that you were plugging a 9 in to the Y equation. And there would be, at least I think that's right. That's what I got. All right. And then the next question was, when will the temperature be 100? So now you've got to set that equal to 100 and solve for T. Now, again, I know some of you don't like to show all your work. You could write that in the red, and that would be good enough too. Assuming you've already defined Y to be that equation at the top, you could just write Y equals 100. Your Y of T equals 100. You're solving that equation. Because remember, on the AP test, if you use your calculator to solve an equation, you have to have the equation written on your paper that you're solving. Okay? But this would do it. If you just wrote that, if you've already defined Y, that would communicate that. All right, and I think I got something like 30.414 minutes. All right? So, you're going to need to mimic that process on a couple of problems in today's homework. All right, or your homework for the morning. All right, that Newton's law of cooling. And then I'll go through that a little bit in the video that you'll be watching tomorrow. Okay, so that's basically it, right? It's going to be solving this exponential. It's going to be having these initial conditions. It's going to be just pretty much what like what you saw right there, and guaranteed to be a question on the next quiz about Newton's law of cooling. Okay, that will look very much like this. Yes, ma'am. Yeah, it's a good question. Typically, I mean, it wouldn't have to be, but yeah. I mean, you could actually have some sort of exponential decay kind of problem or something like that that wouldn't have to be a cooling, right? This equation doesn't always have to involve cooling of a liquid or something. So it could be something over days or years or whatever, you know. But that would be clear in the problem. All right. So let's talk about the second thing then. Let's talk about the second thing that we have to do, which is this idea of slope field. So, we have a special type, hey, I missed too much water. Although we forgot to record a little bit at the beginning. When we were going over some of the homework in the packet. What was that? It is. Yeah. All right. So we actually what we did, Kelsey, is we just got done going over something called Newton's law of cooling, which is a differential equation problem solving. So I'll explain that to you. How'd it go, by the way? Did you have to talk?
No.
Oh, so you got free lunch and didn't? What's that? He did. All right. They were at the Loper lunch.
Free lunch.
We have time. All right. So, was the lunch good? Well, you can't go to UNK event without seeing 15 runs of sign, so that's surprising. All right. Slope fields. So here's what we're talking about. So we're talking about, so Bree, I just tell Kelsey, we're talking about two different things here today. One is Newton's law of cooling, which we just finished, but now we'll get into, and this is a harder one, so I'm glad you guys made it. So slope fields is a graphical approximation to the solution of a differential equation, a graphical solution, but it's just an approximation. So the example I gave was this situation here, okay? When we did this back in chapter 1. So we're going to do this again just to review. So when we did this in chapter 1, when I give you an f prime graph, that's kind of like giving you a differential equation, right? Differential equation is an equation with derivative in it. The solution is the original function. So in this case, I give you f prime and I'm wanting f. So it's kind of like solving the differential equation. So let's go through it. So I'm going to draw my solution here, my f graph, and where do I start? Yeah, we don't know. So let's pretend, just like on Newton's law of cooling that we just did, let's pretend that I gave you a starting point. Okay, so I told you f of 0 is -4, just like on Newton's law of cooling, I gave you y of 9, y of 0 was 190, and y of 4 was 170, right? So let's do that. So I'm going to give you this. Well, that tells me I'm going to come down here and I'm going to start down here at -4. All right. So now we look at the f prime graph, and I notice a couple of things. Now remember, this is f prime. What do I care about on f prime here? Remember the chart connection. I care about the y values here. And what are they? Positive. I care that they're positive because that means f is increasing. What else can you tell me about f prime? Right here. Yeah, but concave, I don't remember concave down of f prime telling me anything about f in the chart. Did it? I don't think it did. I don't think concave down mattered. Increasing is what's happening. Remember positive and getting more positive? Remember that? So right here, this graph is increasing. When f prime is increasing, what's f? Concave up. So what I'm about to draw has got to be increasing and concave up. Okay, and so that's going to happen, let's say, till about there. Do I really know how far up to go? I really don't, do I? Right? Because I don't even know what these y values are. So I don't know how steeply it's doing all that. Okay, now what happens here to the y values? Well, okay, I've got an inflection point down here on f, but what's happening to the y values here? Positive and getting less positive, right? Which means my slopes, because remember, these y values are the slopes of what I'm drawing, right? So I've got positive slopes, but they're getting less positive, right? Now, are they flattening out here? Oh, wait a minute. Yeah, that's bad, right? They don't flatten out. Why not? Yeah, because this doesn't get down to 0, right? So positive and getting less positive, but they're still positive. So the graph is kind of bending down, concave down, but it doesn't quite flatten. And then they positive and go back up again. So that means this graph is concave up. This is bad drawing, but concave up till about there, right? And that's true. Remember, we did talk about how the local max and mins of f prime are inflection points down here on f, right? So we're seeing that. We're seeing a bunch of inflection points. Okay, now we got positive and going towards 0. So positive getting less positive and going towards 0. So now it is going to flatten finally right there. Then we've got negative and getting more negative. So this graph's going to, right, go down, right? So negative and getting more negative. So that graph's going to go down, 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 and being concave down because it's more negative. And then finally negative but going back towards 0. So this graph's going to decrease but go back and level off there. Something like that. Right? Now, So when we were doing that in chapter 1, we were kind of solving a differential equation. We were finding the original function. Now, here's my question. How much do you trust those y values on that f graph? Right? I mean, yours might be pretty good, but that one's awful, right? And what did we just do? We just got done solving Newton's law of cooling differential equation, and we wanted to know what's the temperature at 9 minutes. We wanted to know a y value when x was 9, and we wanted to know it exactly, 3 decimal place accuracy. And we found it. Why? Because we knew the solution to the differential equation. But if I ask you to go on this f graph, even when I gave you a starting point, if I told you to go out to 9 and find the y value, again, trustworthy? Not at all. This is an approximation of what the f graph would be, but it's not a very good approximation at all. Okay, so what we want in a slope field is a graphical approximation to the solution, which is kind of like what we just did. But we want a better approximation than what that was. So that's what we're going to be doing here when we do a slope field. Trying to draw the f graph, the original graph, but make it be better than what we just did there. So here's how it's going to work. All right, so let's go ahead and start with this one right here. It's a simple one. It's one we would be able to solve, which we'll do in a second, but I'll give you a chance to write this down. Make yourself a little bit of a grid like I have here, a little bit of an XY axis. Make the lines nice and straight like mine are. Okay, the differential equation is y prime equals 2t minus 1. Sometimes we use t in our differential equation, sometimes we use x, right? The graph I'm about to draw is y, the y equation, the y function. Okay, now the difference here is in chapter 1, all we had was an f prime graph, so we didn't have exact values of y prime or f prime. We just had the general shape of f prime. Now that we have an equation, we can actually find y prime values, which means we can do better than what we just got done doing. So that's what I'm going to do. I'm going to find some actual y prime values. For example, I'm going to find y prime at 1. Right? Now remember that t is, so that means t is a 1. What do you get? You get 1. 2 times 1 is 2. So I'm literally going to plug in to the differential equation and find what the slope is. We never did that when we were doing the graph. We didn't find exactly what the slope is. We just said, well, it's positive and getting more positive. That's all we did. Now, how can I translate that over to here? Because I'm not going to plot that point, because remember, this is y prime, this is y. Yeah, what we're gonna do is, what I know is when x is 1, or t, I guess, when t is 1, the slope is 1. So I'm gonna draw this little, we call it a slope segment. I'm gonna draw myself a little slope segment that looks like it has a slope of about 1. Now, is this the only place on the graph where t is 1? T, now, it's a little confusing because our t and our slope are both 1. Is there other places on this graph where t is 1? What about right there? Is t 1 right there? Yeah. So wouldn't the graph have a slope of 1 right there? Or wouldn't it have a slope right there? Now, I know what you might be thinking is when you actually draw the function, it can't hit all these different places, right? But we don't know where it is. Remember, we don't know where the solution is up and down, right? So what I do when I draw a slope field is I plot these little slopes and I draw these little slope segments. We're actually going to do this. Now, on our homework today, I don't think you're going to have to. Tomorrow's worksheet, I'm going to give you some grids with a bunch of dots on them, and you have to literally calculate these slope segments and draw these little slopes like this. On the AP test, they have problems like this on the free response sometimes where they give you this grid and you've got to go do it. Okay, now what's another one? Well, how about at 0? Let's put a 0 in for t. We get -1. So that means here on the y-axis, everywhere on the y-axis, my graph is going to have a slope of -1. So I just draw something that looks like it's about a -1. All right, let's go over here to, let's put a -1 in for t. What do we get? -3. That's really steep. You know, it's hard. At some point, it gets kind of hard to draw, right? I mean, how do you distinguish a -3 slope from a -4 slope? Well, you usually don't, right? You just kind of do the best you can. But it's definitely steeper than what it was when we drew our -1 slope. And let's just do one more column. We call these slope columns. Let's put a 2 in to y prime, and we get 3. So over here at 2, when the input is 2, we're going to get pretty steep. So now remember what these red marks are. These red marks are the slope. So it's kind of the shape of the graph, right? But we don't have the graph in there yet. Now, I said that this was one of those easy ones that we should know just how to solve. All right? So in other words, couldn't we just do an antiderivative on this one? What's the antiderivative of this? Oops. T squared minus t plus some constant. So the y graph should be what shape? Should be a parabola. Do you see a parabola in there? Can't you see it, right? In the red, you can see it. Now, if I would have given you an initial condition here, let's say I just said y of 0 equals -1, right? Let's say I'd have given you that initial condition. Well, that would have been right here, right? So what would I do? I'd go down, but it's got to turn around, right? Because then it's got to go up. You see what I mean? What I'm trying to do is follow the red, kind of what I usually say is go with the flow, right? Go with the flow of the red line. So it would go down, but then it's got to turn so it can go up, and then it's going to go up steeper, and then over here it's going up, but then it's going up steeper. But, right? Yeah, but still, wouldn't this be a little more trustworthy than what we were doing before? Because we actually calculated some slopes. So the red lines really are kind of the shape it should be when it goes through that region. And so there would be our solution. A different initial condition would have a different one. Okay, so I said that these are like slope columns. So what happens is the slopes don't change, right? They only change when you go across, because what happens is every time I move to a new t, so right here there's an x value, right here there's an x value, right here there's an x value. So every time I move across to a new x value, I get a new series of slopes. What would happen if I would give you, because one of the things you're going to do in your homework today is a matching kind of thing. What would happen if I had this as my differential equation? Now when I plug in to calculate my y primes, say I plug a 1 in. Now when I plug a 1 in, it's going to go in for the y. So now when I put a 1 in, I get the slope is 3, but that's when y is 1. Well, that's across here. You see what I mean? So what I would be doing then is I'd have a slope of 3 here, and 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 a slope of 3. Does that make sense? And so now I would have not a slope column, but a slope row, right? If the differential equation had y in it instead of x. And then you get differential equations that have both. You get y prime equals 3y plus x. Well, now every time you go to a different point, you'll get a new slope. Those are the hardest ones to draw because you have to just calculate so many more things. And they get kind of strange. I want to show this on your calculator. So go ahead and get your calculators out. And let's pick a new one. Oh, you guys that just came in, did you get logged in? Would be good. Okay. Who should we pick? Let's take the names off. Let's take the names. Okay, here's a good. Who is it? Oh, it's Chris. Well, we can't make Chris do it again. All right. Mitchell. Thank you for volunteering. All right, now, so let's go into your graph screen. Let's go into your graph screen, and let's go ahead and delete that out. Okay, and let's go ahead, and everybody else can play along here. Although we're not going to do much graphing of differential equations, so it's not a big deal on the calculator, but it's a cool way to see some slope fields pretty quickly. All right, so go to menu in the graph entry section, and this time we want number 7, differential equation. So I'll go pretty quick on this, but it's not, like I said, it's not imperative that you have to be able to graph these right now. All right, so let's put in our differential equation. It was 2t minus 1. However, before you hit enter, Mitchell, notice down here, right here, it's got our initial condition, and notice they use x. So in differential equation mode, we have to use x. Now notice, in function mode, we had to use x. Differential equation mode, we have to use x. In parametric mode, we had to use t. So we got to keep that straight. So change that t to an x. We have to do 2x minus 1. Okay, go ahead and hit enter. This kind of messed up in the other class, but now, our window's not very good here for this one. Okay, so we're not getting to see much here. So let's go to our window under the menu. And let's go to window settings, it'll be fine. Go to our settings. Let's go -2 to 2 on our x. And let's go about -5 to 5 on the y. Oh, see, this happened in the other class. This is the weirdest thing. Are you guys getting that? What do we do? Because what's wrong with this? Well, your window. -2 to 2 for your x. It's flipped. The vertex wasn't supposed to be over here, but this happened in the other class. So Mitchell, go, and I don't know why. Go ahead and go hit tab or whatever so we can get into there. -2 to 2 on the x, Ryan, and -5 to 5 on the y. Now, see, then it changed.
It's in the middle.
And all of a sudden it changed, which is bizarre. Okay, so go ahead and hit enter or tab and get that out of there. Okay, let me see your equation. Hit tab. There we go. You have something to do with the ones. Okay, hit enter. Go to your window. Oh, now it's right. See,
I have to.
This is weird. Okay, anyway, I'm not quite sure what's happening there, but some software glitch. All right, so isn't that kind of what we had, right? Isn't that very similar to what we had? Now, it's got more segments. The calculator can do it very fast, and so we can see it a little better. But can't you see the parabola there, right? You can see it. Now, let's put in that initial condition. So go ahead and tab again, Mitchell. Let's go ahead and tab and get back into there. And here's where we put our initial condition. So we had 0, -1. So 0, -1, and we hit enter, and it throws in our solution curve for us, right? Like we drew. Now notice it doesn't connect the dots, and the reason for that is it's not actually finding the solution curve equation. All it's doing is plotting points based on those slope calculations, and it's using something called Euler's method. Euler is the name of a guy, E-U-L-E-R. And we're going to learn more about that later, how those calculations are actually being made. But for right now, that's our solution curve. Okay? So let's show some of those changes we were talking about. So here's where we talked about a slope column, right? You've got, every time I change to a new x, I get a new slope. So this differential equation only has x's in it. Now, Mitchell, go to the tab up there to the equation, and instead of 2x minus 1, let's make it 2y minus 1. Now, when you type the y, hold on here a second, you actually have to type y1 because this equation is y1 prime, so we actually have to type y1 there. So go ahead and type a 1 after the y. Yeah, y1. We have to just type y1 there. Okay, so that's something you got to be careful you do if you're ever graphing a differential equation. It's got a y in it. You have to do y1 or y2, whichever one you're on. Ryan's would be y3, right, because you're on that. Okay, hit enter. And notice how it's changed now. They're like rows, right? Now, when you go across, they don't change. But every time you go to a new y, right, every time you go up and down, you get a new slope. So this one has y's in. Okay, one last time here, Mitchell. Let's change that to, now go, instead of -1, let's go -x. So now this one has an x and a y. And hit enter. And then notice how you get some weird things. In other words, when I go, well, wait a minute. Yeah, like here, when I go to a new x, as I go to a new x going this way, I get the slopes change. And also when I go up and down, the slopes change. Now up here, they don't seem to be changing much. But over here, they are. So you get kind of some strange things happening there. Okay? So that's when you know you have both x's and y's in there. All right. So go ahead and get your books out and turn to page 217. And we're going to kind of wrap this up here and get you started kind of working on the homework here a little bit. I feel like I'm kind of missing something there. All right, so for tomorrow's homework, you're not going to have to sketch these slope fields, but for you guys that are going to be gone tomorrow, anybody else know they're going to be gone tomorrow? Kelsey and Bree, I know you're going to be gone tomorrow. Okay, so Brock, okay, I'm going to send you guys, well, actually I'm going to send to everybody the calculator document we need for tomorrow, and then I'll give you guys that are going to be gone the worksheets that go with it too. Oh, you're coming to second, okay. So this is tomorrow now, again, since I won't be here. But you can see right on the front of the page, right, it's got some graphs with some dots on them, right? And what you're going to do is you're going to be graphing some slope fields, like what we just did right there with those red segments, okay? So that's some of what you're going to be doing tomorrow, and I'll be sending that along here in a minute. On today's homework, there isn't any of that. But let's take a look at problem number 7. This is on page 217. And, all right, here I believe is problem number 7. Right? You everybody see that on page 217? So you've got these slope fields here. And if you look at the bottom left corner of page 217, it's got a series of differential equations. Some of them have y's in them, some of them have t's in them, some of them have both y's and t's. What your job here is, on 7 through like 14 or 7 through 12 or, I don't remember how many, on 7 through 14, your job is to match those slope fields with the equations. And again, tomorrow's worksheet has some matching too, and on our next quiz there will be some matching for sure. You'll have to draw slope fields, and you'll have to do this matching thing as well. Okay? Well, let's look at this. How can we do this matching? Well, first of all, let's eliminate by looking at the slope field and seeing, is it going to have y's in it? Is it going to have x's in it? Or is it going to have both? What do you think on this one? Okay, so I heard both, I heard just t's, and I heard just y's. Okay, those are the three choices. All right, here's what I would do. When you go across, do things change? No. Okay, but what's that mean? That means that every time you move up and down to a new y, you get a change. That means when you plug in a y, you're going to get something different, right? Every time it changes. So going up and down, if it's changing, that means you got y's in it. Going across, does it change? No. As I go across from new x to new x to new x to new x, right, the slopes never change. So there's no x's in there, no t's in there. So which one of my options have just y's in it? There's y prime equals cosine y. There's y prime equals 1 minus y. Okay, so those are my only options. So it's got to be one of those three. Now, how can I narrow it down from there? Let's plug some numbers in. Let's plug some y numbers in. Now, 0 is always a good y number, a good number to plug in. So, because right here, at this point right here, right, y is 0. So if I put in here cosine of 0, that's 1. Does that look like a slope of 1? It does. Put a 0 in here. Oh, okay, well, could be one of those. We'll put a 0 in here. 0. That's definitely not it. Okay, so now I better pick another point. Well, right here I notice that the slope looks flat, which would be a slope of 0 right through here. Now, where is that? Well, this would be about 1. So this looks like it's about 1.5. So if I do 1 minus 1.5, that doesn't look like negative 0.5. But let's double check this one. What's cosine of 1.5? Maybe it's not 1.5. Maybe it's 1.57. What's 1.57? Pi over 2. What's cosine of pi over 2? 0. I'll bet that's what it is. And notice down here, when you'd have about negative 1.5, if you put negative 1.5 in for y, 1 minus negative 1.5 be 1 plus 1.5, it'd be 2.5, definitely not. So it looks like this is the one. So that's how you do the matching, kind of a process of elimination. All right? Now, if you, oh, let me make a comment about the blue dots. You don't have to do this, but on the quiz we will, and tomorrow's worksheet you'll be able to, because in the book it's hard. You'd have to trace in your book or something. They put these blue dots and they say, assume those are initial conditions, sketch the solution curve. Well, on the quiz, it'll be on your paper. Tomorrow it'll be on the worksheet. So you'll be able to practice just going with the flow. So like if I was going to draw this solution curve, I would just kind of do that. Or if my initial condition was this, it would just kind of go up and then just follow. It would just kind of, oops, it would just kind of follow those points. And you would just sketch in your solution curve. Going with the flow once you have an initial condition. All right, very quickly here. Then on number 8, is this one going to have just x's, just y's, or both? Just x's. Every time we go, or t's, I guess. Every time we go across to a new x value, the slope seems to be changing. Okay? And then what about 9? 9 is one that would have both. When I go across to new x's, I get new slopes. When I go up and down to new y's, I get new slopes. This has to have both here. So that's how you can, kind of see what's going on, and then you'll have to plot some points and kind of match that way. All right, and I've got a new thing I've got to hand out to you on the assignment sheet here. All right. Matter of fact, let me pull that up, and I'll hand it out later, but let me pull it up here so you can just copy these down. All right, so our homework is this first line up here. All right. Now, 23 and 24 are the ones that are going to take you the most time. That is the Newton's law of cooling problems where we have to solve those differential equations. Okay? Where we have to solve the difference gradient and plug the numbers in and find that stuff. So 23 and 24 have multiple parts. You'll have to work that out and so forth. All right. 3 through 14 then, well, 7 through 14 is just the matching, right? And so that's not going to take a whole bunch of time. And then let me just talk real quickly about 3 through 6, because the wording is just bizarre on 3 through 6. On 3 through 6, they say, find the equation of the tangent line. But they say it in like 4 different ways in the 4 problems. One, it says find the equation of the tangent line. The next one says show that this is the equation of the tangent line. The next one says verify that this one's, they're all the same thing. Now, what do you mean equation of tangent line? Well, what do you need? You need a point and you need a slope. Well, think about in these problems. Won't you have that usually? You usually have an initial condition, so there's your point, and you have a differential equation which you can plug into to get the slope. So, equation of tangent line problem. So, that's all you're doing on 3 through 6. So what I would do is if it says verify or show or whatever, I would just find the equation of tangent line and be done. All right? Good enough. All right. So, a couple of cleanup things just because I'll be gone tomorrow. So let me send you this document. All right. So I'm going to send this to everybody. So hopefully everybody's logged in. And it looks like it went to everybody. It's called Slope Fields Forever. Did I do that already?
Yeah.
I did that at the beginning. Oh, but these guys weren't here, so that's okay. So you just got it again. What's it say? Does it ask if you want to override it or something? It just said all files are transferred? Oh, okay. All right. So you guys have that document now to go along with that worksheet. For those of you that know you're gonna be gone tomorrow, when we start working here, you can come up and grab the two worksheets that I'll be handing out to everybody else tomorrow. Here's the assignment sheet that we'll have for the rest of chapter 4. Okay, so let's recap this. So you've got what you need for tomorrow. You bring your Chromebooks and the headphones. Those of you that be here to watch that video that I showed there, they'll be going over this homework and checking and so forth. Okay, and then Kelsey and Bria can help you guys maybe here with that, what you missed on that news on Coop. Okay, should be good.
4.1 quiz next, like Wednesday.
So the 4.1, I forgot what this says. So yeah, so what we're doing, so tomorrow is those worksheets, right? That I was just talking about. So that's the next line, and then 4.2 is going to be Monday and Tuesday, and then the quiz 4.1, 4.2, that's going to be on Thursday. That's going to be on Thursday next week. And then we have the Calc Carol bonus stuff next Friday. No homework over break. No homework over break. All right, go ahead. You got the rest of the time here to go ahead and get started and get to work.